I mean, this is an amazing time to be a math teacher, I just gotta say, because there's so much math involved here. It's pretty interesting. So the picture I was looking for was kind of the overall count. And there's a lot of grouching from different directions about whether this count is accurate or not. But this comes from the CDC website, and basically, it's a daily count of new cases, and or maybe this is the total. No, these are total cases. Okay, so the reason I want to start here is because the whole concept of exponential is a little hard to fathom in some ways, and this I like this because there was a period of time, I think, in here where things really were growing exponentially, and and then a lot of government bodies, local, county, state bodies, made difficult decisions about shutting down people's activity, and that did have a positive impact in terms of stopping the growth from continuing to be exponential. Because the crazy thing about exponential growth is there's this problem that I've heard. I don't know if you've ever heard. It's about folding a piece of paper over 50 times, and how thick the paper would be if you were really able to fold it 50 times. Um, and it's kind of mind-blowingly thick, and that's because with exponential growth, you get the multiplicative factor increasing things. Once you get really into it, it starts really taking off. Okay, there's another example of like the grains on the chessboard where the king gives him 1 grain of rice and then 2 grains of rice and then 4 grains of rice, and because there's 64 places on the chessboard, it ends up being an incredibly large number, which I'll just let Excel calculate for us here. Right, this is the pattern where we go 1, 2, 4, 8, 16, and you're like, well, yeah, I can see that's growing pretty fast, right? But where do we get to if we go all the way down to the 64th place on the chessboard? Because the chessboard is 8 by 8, and the answer is that we end up with 2 times, or sorry, yeah, 2 to the 64th power. And this number here, you know a little bit about scientific notation, so you can imagine that this is a fairly large number. Actually, it might be 63rd power in all fairness, not 64th, but whatever. It's still 10 to the 18th, right? Remember, this is 9.2 times 10 to the 18th power. And that means we're talking about, just because it's worth looking at the size of this number, we started with this very sensible little growth pattern, and by the time we went through it 64 times, we ended up with this enormous number. So true exponential growth gets out of control very quickly, which is one of the reasons why people were freaking out about the coronavirus. By people, I mean scientists and epidemiologists, and then that was taken up by the media. Now, you can argue about whether the media had an appropriate reaction or overreaction or whatever, but the reality is if something is really growing exponentially, you're going to have a problem pretty soon. So let's take a look at this data and talk about what indicates that it was exponential. Now, I actually don't know when this was most exponential, so I'm really just kind of putting myself out on a limb here and saying, I'm going to say middle of March was kind of the period of time when it was most exponential. And I want to show you what that means, because although there is a question that you're generally asked where you need to identify whether this is exponential or linear. But I think this is an important just life concept that's not too crazy to understand. I'm going to use my special transpose pasting. I'm also going to rename these days after 3-7. So this is going to be 0, 1, 2, 3, 4, because actually dates are complicated bits of information with lots more than what we can do. So I'm going to go ahead and graph this, and then we're going to go ahead and look at, is this exponential or not? And what is it that tells us that it's exponential? Okay. So the first thing, and I'll zoom in a little more here. The first thing I hope you notice is that it doesn't look linear, especially at the right side of the chart, right? If I got rid of this part of it, then I could kind of convince myself that it actually is linear, right? I'm gonna cover that up. I could say, oh, that looks kind of linear. And that's another important thing about exponential growth, is that in the beginning, you might not really be able to detect it by the eye very easily. So it's only when you kind of get into it that it's like, whoa, this is taking off. All right. Now, what is it mathematically that makes this exponential? Well, if we take the relative change, let's just apply absolute change and relative change. And we're going to go just using these numbers here. I'm going to do this with Excel, and I want to show you one of the Excel tools that I think you're going to want to use, which is autofill. I may have already introduced this, I don't know. But absolute change is new minus old. So I just need to take the number here and subtract the number there. And I'm going to go down here. Those are going to be my 9 absolute change numbers, right? This is just new minus old. Just to show you that again real quick, I made a calculation here and I used cell references. And then I went to the bottom right corner and I clicked and I dragged from there. And Excel basically rewrote my formula 9 times using what I had written in the one above. So it kind of does this predictive thing where if you're using a table, you just, put the first one in and then you do that autofill down in it, and it recalculates everything for you. So that's a nice feature. Okay, let's look at relative change. Relative change is new minus old divided by old. Now again, I'm going to use the absolute change and I'm going to divide by the old value instead of doing new minus old divided by old, just because there's more likelihood of making a mistake there. So what this is saying, just remind ourselves, is that 144, which is the absolute change, was about a 50% increase from the day before, right? So if I look at the relative changes I go through here, it's actually pretty variable. But what I would expect to see is, sorry, let me just write this formula to be consistent. If this was truly exponential, I would expect to see that the relative change is consistent, that it's always the same. Okay, so this is, again, going to be sort of quasi-exponential. We can try to write an exponential model for it, but in reality, it's because this is real data, it's much more complicated than that. And so any model that we come up with is just going to be an estimation. But you shouldn't feel that terrible about it, given that I hope you looked at the data. Oh, it was back here. You looked at this data and you thought, yeah, I can make a line through this, and that would be a pretty reasonable thing to do. It's the same thing we're doing here, looking at this picture. We're saying, yeah, we've got data that seems to be, especially to the right side, kind of taking off exponentially. And so, this is 50% change, 50% change. Okay, this is only 45% change, and some of these are lower, like 16, 17% change, but then I'm back to 50%, 60%, 50%. So that's the justification for thinking of this exponentially. In basic terms, I want you to know that linear change, you expect to see a constant absolute change. for exponential change, you would expect to see constant relative change. Now, in an exponential model, I don't know why they don't provide this for you in your formula sheet. We use a different form, okay? This is an exponent, and the exponent, remember, if you haven't thought about it in a while, right, 2 to the third means 2 times 2 times 2. The 3 is the exponent. It's telling you how many times to multiply the base. The base is the number on the left. If we're going to write it out the way it would look on paper, we use subscript. So it'd be like 2, I don't know if I can even get the font here to be what I want it to be. It's not worth time to do that. Okay, so the reason that exponential change is constant relative change has to do with the multiplier. Because if you think about something that's like a 10% increase, what's the multiplier for a 10% increase? Taking us back to Wednesday here. Well, you just took a quiz on it today, but how do we find the multiplier for a 10% increase? You guys remember how to do that?
You added to 100, so it'd be like 1.1.
Boom, 100 plus 10 is 110, that's 110%. So the multiplier is 1.1. Cool. So the point is that if I keep increasing something by 10% over and over, all I have to do to make that happen is continue to multiply by 1.1. So it's the same thing that was happening with the rice, and we're doubling it, right? We're continuing to multiply by 2. We started with 1, and then we multiply by 2, and then we multiply by 2, and then we multiply by 2. That's exponential growth. Now, the multiplier 1.1 is not as significant as the multiplier 2, but it still leads to the same effect, which is this curve that goes up. And I can show you that here. Let's say that we have a town, and the town has 90,000 people in it. And that's in the year 2000, right? And then for whatever reason, this town just sees exponential growth. So this times 1.1. And then the next year, the same thing happens. It increases by 1.1. So if I continue this pattern out, and I do it for quite a number of years, then I'm going to end up with an exponential curve because it's exponential growth. And at the beginning, it might look kind of linear, right? If we, again, cover up, and I can't cover up the screen with my hand the way I could in class, but if I cover up the beginning of that, you might say to yourself, well, I could kind of see that would be linear. But the point is, as it goes on, the curve goes up. That's what exponential growth looks like. And exponential growth is really foundational to one particular industry, which is the financial industry. And so that's where we're pivoting to next, starting on Wednesday. But your tasks for exponential growth are similar to the ones for linear, which is why we're talking about them together on the same day. I want you to be able to make a model based on some words. And then kind of the secondary task is, if I give you some data that grows, you should be able to identify whether that's exponential or linear and then make the model based on that. Okay, so let's work on the first part. Think about how the model gets created. World population is currently 7.3 billion, and it is growing at 1.1% per year. Make an exponential model for this situation. Okay. So this problem is a good starting point because I think it highlights the similarities between the linear and the exponential, which is we're still looking for the same two questions. How is it changing? And where did it start? The structure is different because we're using y equals a times b to the x. And in this problem, you don't have to figure out that we're using the exponential model because it just says straight up, make an exponential model. And I think that's pretty fair to what the test would expect you to do. That it would give you a situation, but then it would say, make an exponential model for this situation. So you do have to be able to recognize exponential and say, oh, hey, that's not linear, right? The model is being used in both cases. So A is the starting point, and B is what is the multiplier. And I'm going to use the word multiplier specifically because that's the work we did in the percent change section, right? So I'm hoping that when you see 1.1%, you're not going to say to yourself, oh, the multiplier is 1.1. That's a common error. The multiplier is the process by which we change percent increase or percent decrease into a number that multiplies, and then that would affect that change for the number. So this is the percent increase or decrease turned into a multiplier, the growth rate. Okay, and you could have either situation, so don't assume that it's going to always be an increase. Right? It could be very well be a decrease when you come to do this problem. So let's talk about what we can do here to finish this question, because we're just trying to make a model. We're not doing any calculations, not doing any predictions, although we would want to be able to do that. So what are you going to put as the first number?
$7.3 billion.
Right. And you got to make a choice here about whether you're going to write that out or whether you're just going to say 7.3 and remember that this is in billions. Me personally, I'm going to say 7.3 because writing out all those extra zeros is just going to make my model harder to use. I'm not ignoring the billion. I'm just saying, okay, when I calculate anything, it's going to come out in billions. All right, now what about the multiplier? This is the hard part. Because I've got to apply the multiplier process that I did before.
1.011.
Nice. Okay, and again, if you're confused about where that stuff comes from, we just need to go back and we need to practice more on that multiplier process. And I just posted the video yesterday, so you can go back and look at that again if that helps. And if you want to practice more on the side, I'll give you some more questions. The multiplier concept goes throughout this unit, and so it's super important that you feel good about that, you feel confident about that. Now, I did finish the model for you. Close the parentheses, superscript. That's what an exponent looks like. Okay, let's do another one. So 30% I just made up, but I'm kind of mentally averaging, okay, we had some 40% and 50%, so we also had some 17% and 20%. So, you know, take a number in the middle, and let's use that to kind of come up with a rough model here. So they were growing by around 30% in mid-March. Now, let's just take that last date. Where was it? Sheet 8? No, sheet 5. So there were 10,000 cases Yeah. Okay. So 318. Oh, shoot. What would the total be today if the growth had continued at 30%? Now, there's a couple of challenges in doing the math for this problem. But again, I want to try to make something that's fairly realistic, relevant to our situation, also uses that skill we just talked about. So that should really be your first step. You should not be trying to do this by just doing a bunch of calculations. You should be making a model and then using the model to finish the problem. So that's where I want you to focus your attention right now, and I'll give you a minute to do that. What number would you put in for A, and what number would you put in for B? Remember, A is your starting point. B is multiplier, the growth rate. Okay, just gonna give you a minute for that. Don't say anything out loud. Let everybody have a chance to think about that. I'm gonna get another. Okay, what do you got?
I got y equals 10,000.
Okay.
And then in parentheses, I got 1.3. And then, yeah, that's it.
Do that
Or X.
in for X. That's the next problem, really. That's the sub question we got to deal with. Sub question's a term I haven't brought up yet, but it becomes kind of an increasingly helpful construct as you do harder and harder problems in math, which is, what do I need to answer in order to get to the answer that I eventually want? The sub question here is, how many days have passed between 318 and 329? Is that where we are? Sorry, 629? Did I get the date right? It's hard to keep track of. Yeah. Okay. Now, I'm not going to that I would ask you to do. I will show you something cool, which is the Excel can do that math. No, God, Excel made me a liar. let me do it a different way. I believe in Excel. June 29th, March 18th equals boom minus boom. Come on. 103 days. Okay, so that's what I would use as my X value. It might be 102. We have to kind of think about what the exact right number is, but it's not going to make that much of a difference to get hung up on it. I'm interested in what would happen mathematically if I put 102 into that exponent. Now, this is a good opportunity for you to practice using exponents because up to this point, everything's been multiply, divide, add, subtract. And this is our first real okay, well, we got another operation that we need here. So can you do on your calculator an exponent? Now, also order of operations, that exponent needs to happen first, 1.3 to the 103rd power, and then multiply by 10,000. And that will give you your prediction for how many cases there would be total in the US if it had kept growing at 30%. I'll say it out loud and give everybody a chance to out your feedback about where the exponent is on your particular calculator because it's different for everybody.